So a lot of them are familiar because we did this with these same problems roughly when we talked about reference angles and things like that, right? And I mentioned last time that these, I don't really like these examples, so I'm just going to toss them. All right. So if they're not one of the special angles in the unit circle, you'd use a calculator for it. All right. So for our purposes, at this point, we just want to focus on the special angles. All right. Now, it's up to you, but I tend to want to draw a diagram. Now, me personally, because I've done this so many times over so many years, I already know what the answer is, but I'm kind of looking at it from a student perspective. And how would you go about doing this? Right. So there's a couple of ways to handle it. One would be to look at the unit circle. The other is to express it as a function of a positive acute angle and then find the exact function value. Right. The benefit of this approach is that you really only need to know the first quadrant values. Right. So some people don't like doing it this way, but I figured I'd present it at least once. All right. So 225 would put you in the third quadrant. All right, that's Q3. By starting at 0 and traveling here, we've gone 180 degrees. To get to 225, I'd need to go 45 more. All right, so it's a 45-degree reference angle in the third quadrant. Now, tangent, based off of ASTC, all right, tangent is positive in the third quadrant. All right. So what that tells me is that tangent of 225 is equivalent to the positive tangent of 45. All right. Now, if you happen to know the tangent of 45, that's great. You're done. Right. But if you don't, we know, or we talked about this last time, tangent is the same as sine over cosine. All right. So if I know my first quadrant, the first quadrant of the unit circle, I've now taken this and made it a function of a positive acute angle. I can just use that information and go from there. All right. So I'm just going to sketch out the first quadrant. You got a glimpse of what my handwriting really looks like there. I don't know if it's going to let me do oh, it did. Okay. So we have 1, 0. That's at 0 degrees, 0 radians. Now, of course, I wanted to screw that up. Let me get it in there. Going to draw 3 line segments for our special angles. All right. So this is rad 3 over 2, comma 1/2. That's 30 degrees, pi over 6 radians. A little notation for radians, you could write it as a power of r. I mentioned that last time. You could just also write pi over 6 or pi over 6 rad, whatever you want to do there. Rad 2 over 2, comma rad 2 over 2. That's at 45 degrees or pi over 4 radians. All right. Then we have 1/2. Oops. Put the cart before the horse there. Or the number before the parenthesis. All right. 60 degrees, pi over 3 rad. Right. And then the last one here is 0, 1. That's 90 degrees, pi over 2 rad. All right. So that's a lot to write out just to answer one question. But if we use this function of a positive acute angle approach, we can use this first quadrant over and over again. Right? Because basically we're taking whatever the trig function is giving to us and writing it so that the angle is a first quadrant angle so that we can kind of live in this neighborhood. All right. So sine of 45 is rad 2 over 2. I use a highlighter. Sine of 45, that's this value here because it's cosine comma sine. also turns out that cosine of 45 is also rad 2 over 2. So that's this value here, which simplifies down to 1. All right. Now, again, I mentioned this last time, and I gave the whole example of how when I was a student, I just used the calculator and I kind of figured it out from there. But then later on down the line, I realized, you know what, I better actually get a good handle on this. Right. So this is an attempt to get a good handle on it. But that being said, I'd like to check my work. Tangent 225, 1. Tangent 45, also 1. All right. So not only does that tell me what the tangent of 225 is, but it also tells me that it's equivalent to the tangent of 45. Right. And you kind of look at that and say, well, why did I do all this work? And it's a valid question. Right. At this point, you just have to believe me that I'm telling the truth, that it's important that you learn how to do it using the unit circle, but you're not really truly going to believe it until you're in the situation where knowing it pays off. All right. So I'm actually going to use this a few more times. I'll just kind of put it in the middle. Cosine of 405. So again, quick sketch if you want. You could also just subtract 360 or add 360 depending, and that'll tell you, all the other equivalent angles. As soon as you get one that's between 0 and 90, you're pretty much done. All right. So this is 360. I'd have to go another 45 degrees to get to cosine. All right. That puts me in the first quadrant, which means that cosine of 405 is equivalent to cosine of 45, which we learned in the first problem there is radical 2 over 2. All right. And again, numworks is really nice. It just flat out tells you the answer, in decimal form and in simplest radical form. All right. So again, it really makes it difficult to believe that I'm telling you the truth, that you're going to need to know the by hand way of doing it. But, at least you have the calculator to fall back on. All right. Negative 120, quick sketch. Negative is this direction. So 180 would be here. That's too far. I don't want to go that far. All right. So I want to go 120 degrees. Not going to autocorrect on me. All right. So 120 degrees put you about right here. All right. That's in the negative direction, which means that we had to go 240 degrees all around. But remember, I want the reference angle. Right? That'd be this little guy here. So I can look at it and say, if I go 240, I'm going 60 beyond 180. Or I can look at it as, if I'm going negative 120, what's it going to take to get me back to the x-axis? Another 60 degrees. Right? So either way. Now, ASTC, in quadrant 3, tangent is positive. So this would be equivalent to the tangent of 60. All right, tangent of 60, well, tangent is sine over cosine. So sine of 60 over the cosine of 60. So then I'm looking at my unit circle, or at least the first quadrant of it. Sine of 60 right here. And let's get a fresh new one, maybe a nice light green. For those keeping score at home. Cosine of 60 will put you right there. All right, so we're looking at rad 3 over 2, 1 over 1/2. A complex fraction with a common denominator. So fraction over a fraction where the denominators are the same, they cancel out. You're just left with a radical 3 over 1, which is the same as just saying radical 3. All right. So check it in your calculator. Tangent of 60, radical 3. All right. So it's a nice mobile answer key. Now, I suppose you could do the same thing with the operations. tangent one, like just type it right in, tangent 135. That would be plus sine of 330. It'll tell you negative 3 over 2 or negative 1.5. But again, we want to get to a point where we can do this quickly and easily, right? And if you want to, I mean, a lot of people do this. They just have a big old unit circle open right next to them, and they just reference, right? So tangent of 135 is the same as the sine of 135. So I'm going to do this with the unit circle now rather than the method I just showed, because I want you to have the flexibility to go either way, knowing that in the future, you're going to want to be able to do it either way. All right. So referring to the unit circle, 135 degrees, so I'll go previous page, 135 degrees has a cosine value of negative rad 2 over 2 and a sine value of positive rad 2 over 2. All right. So we could just plug that in. So rad 2 over 2, negative rad 2 over 2. Sine of 330, that's the second to last angle measure in the unit circle, right? So that's the one right before 360. So that has coordinates radical 3 over 2, negative radical, negative 1/2. I want the negative 1/2. All right, but again, reference the unit circle. At 330, we're looking for the y value corresponding to it. All right, that's the sine at that particular angle. So the first fraction simplifies down to a negative 1 minus 1/2, so negative 1 and 1/2, negative 3 over 2, negative 1.5, however you want to write it. Sine of 300, right, has a negative radical 3 over 2 value. That's the y value of 300 degrees. All right. Negative 240 is the same as the sine of 120, which has a value of radical 3 over 2. So this should equal 0, but double check. Negative, positive.
You put in 330 instead of 300.
Thank you. I would have stared at that for the next 5 minutes or so before I realized, if I ever actually realized. There we go. Thank you. Appreciate it. All right. Sine of 60, radical 3 over 2. Cosine of 150, negative radical 3 over 2. Tangent of negative 45 is going to be a negative 1, so minus a negative 1. And again, this one comes from sine over cosine. Now, negative 45 is the same as 315 degrees. All right, so sine of 315 over cosine of 315. So that's how you can come up with a negative 1, because on the top, you'll have negative radical 2 over 2. On the bottom, you'll have positive radical 2 over 2. So it'll simplify to a negative 1. All right, so when you multiply here, this 3 is poor quality, so let me take care of that. Not much better. There we go. So negative 3 over 4 plus 1 is going to be equal to 1/4. All right, but again, sine 60, cosine 150, minus tan negative 45, and you get your 1/4. All right. So, you know, these last three anyway are more complicated than what's on the quizzes, but yeah, it's helpful. When we get to solving trig equations, you'll see what I mean. Right? It becomes even more critical that you know this stuff. All right, but now we're going to shift gears and we're going to talk about areas within a circle, which actually doesn't seem like it ties together at all with any of this stuff, but you'll see in a minute. All right. So the first thing that we're going to talk about is the area of a sector. Sector of a circle is, I kind of have like little mnemonic devices. The sector is a slice of pizza. right? So it's a slice of pizza. So if I draw an angle here, what I'd be looking for when I want to find the area of a sector would be, let me get it in there. I'm looking for this area here. So area of the slice. So that's a fraction of the area of a circle overall. Area of a circle is pi r squared, right? This is going to be a fraction of that. So there's a few different ways that we can sort of derive this process. One is based off of knowing that the area of a circle is pi r squared, but I kind of want to pretend that we don't know that, right? So let me define some terms here. We have S, which represents the arc length. All right. We have theta is the central angle. All right. It's the angle created when you generate the sector. All right. So it's basically, remember, we talked about this a couple of classes ago, where an angle isn't just a static thing, it's dynamic, where we start off at 0 degrees. I got to do it as a resize. And then, oh, why did it work last time? Oh, I know why. I gotta hold on to it. So we start off here and then we sweep through the angle, right? So as we move from this line segment to this one, we're sweeping through the angle, kind of like a radar, all right? Or like radar. We also know that the distance from the center to the circumference in a circle is equal to r for radius, all right? That's something that most people should, know without me defining it, all right? Now, there is a formula that will compute the arc length. So it's not asked for here, but if I want the arc length, that's going to be equal to S, or it will be S equals R times whatever theta is. All right. So S equals R theta. It's getting the product between those two, which is telling us how many radii we need, or what would the overall length of a radius be in order to get a distance wrapped around the circumference of the circle. All right. Now, if I look at this slice of pizza here as kind of like a sort of like a modified triangle, so something like this, we can say the area of a triangle, which is A is equal to half the base times the height. All right. Now, this is really a wedge, but it's triangular in nature and it has the same properties. All right. So the height would be the distance from this vertex to the base. All right. So this would be the height. This here would be the base. Right. So half the base times the height would give us that area. All right. But the base in a wedge is equal to the arc length. The height, that would be the equivalent to taking or starting at that the center of the circle and going out to the circumference. It's going to be a radius. It's going to have the same radius value no matter where we are on the circumference of the circle. Right? It's the same radius value. So if I put it here, that's the same as saying r. All right. So the height has to be equal to r for radius. And we just talked about this. The arc length is equal to r times theta. So the area of the wedge is going to be equal to 1/2 the base which is r theta, times the height, which is r. And that wedge we call a sector. And the area of a sector ends up being 1/2 r squared theta. R squared times whatever theta is, 1/2, right? So you have a formula. After all that, it's like, okay, well, I have a formula now. Can I just use the formula? Sure. Just like to give you a little background from where these, or for where these things come from, right? And just as a kind of a demonstration, the area of a circle. Now we know that its area is equal to pi r squared, but if I use my sector formula, theta has to be equal to 2 pi, because if I'm starting at 0 and I want to sweep through, let's say, this tiny little sector here, that might be like a theta value of pi over 3. If I want to go halfway through, that'll give me a theta value of just pi, 180 degrees, pi radians. But if I want to go all the way around, then I would have to go 2 pi radians. All right. So area of the sector, 1/2 r squared theta is going to be equal to 1/2 r squared times 2 pi. Now, I never told you what the radius was, so we leave that as a variable. All right. So 1/2 of 2 pi is just pi. And so we get pi times r squared. All right. So when we let theta equal 2 pi, we actually get the area of a circle. Because a sector that has an angle of 2 pi radians, or 360 degrees, is equivalent to a circle. Area of a circle, the figure itself would be a circle. All right. So the circle was always there. We just covered more and more area as we worked our way around. Here I'd have 1/4 of the area of a circle. This would be half the area of a circle, 3/4 of the area of a circle, and finally all of the circle. All right. Now, that's all well and good. Now we just got to answer some questions. You'll see the directions say round to the nearest 10th. So that's great news. It means, well, maybe it's not great news. It's fine. It's okay. It's news. Because we just spent some time talking about the unit circle, and now we're not going to use it. All right. Whenever you see round to the nearest 10th, that's your license to not use the unit circle. The central angle is 3 pi over 7 radians. So the area of the sector here is going to be 1/2. They told us the radius is 11 centimeters times 3 pi over 7. All right. So do some number crunching. 1/2 times 11 times 3 pi over 7. It gives us a simplified form, but also tells us that it's approximately 7.4. So it's going to be 7.4. The units are linear units squared, all right, because it is an area. All right, so the linear units are centimeters, so this would be centimeters squared. All right. Sometimes they jazz it up on you a little bit. They tell us that it's 315 degrees. All right. Well, that's 7 pi over 4 radians. We need it to be in radians. The diameter is 8. So that means R has to be equal to 4. Once we pull that information from it, we're good. All right. So the area of the sector, 1/2. Oh, apologies. Sorry. It's 1/2 r squared theta. I don't know why I whiffed on that. This should have been a power of 2.
I was going to ask you that question, like, why am I not seeing that doubled?
Yeah, there we go. 81.5 is what it should have been. Yeah, that's a classic case of the students second guessing themselves because, a teacher probably knows something we don't know. We know enough to know by now that if it doesn't look right, it's probably something that I just kind of whiffed on. Okay, so in this case, 1/2 times 4 squared times theta 7 pi over, my little 4 didn't really take there, 7 pi over 4. And again, just chuck it right into the calculator. And we get about, well, this says nearest 10th. So it's kind of, like the little gray area there, nearest 10th. If I use the 8 to round the 9 up, it's going to go up. They said nearest 10th, so I technically would write 44.0 feet squared, so square feet. All right, so it's really just pulling the relevant information out from the circle, from the information regarding the circle, and then, just popping it into a formula. So that part should be easy. It's not designed to be overwhelming. Some of the word problems that come from this can be a little tricky, but it's not designed to be tricky. It's just tricky by nature. All right. So the sector of a circle, I call a slice of pizza. The segment I call the pizza crust. It's not perfectly the crust of the pizza, but that's what I call it. It's the best I got. All right. So we have the sector, that's the slice. If I were to draw a line segment connecting the two intersection points between the radii and the circumference, I would get a little line segment. That's not the segment that it's referring to, unfortunately, because we're used to thinking of a line segment as really any of these things here. All right. But what this is asking us for is this little teensy tiny area, actually even teensier tinier. Oh, that's going to be too small. Let me go 2 millimeters. 1.95 is close enough. Actually, even that's too big. Just want to get into that little corner there, a little bit. It looks better when I zoom out. But what I shaded in green is the segment of a circle. And what we want to do is find the area of that. All right. So the area formula is equal to 1/2 r squared theta minus the sine of theta. All right. This one I actually can't prove to you just yet because there's a couple of skills we have to go over before we can get to it, but we'll circle back to it down the line. All right. In both cases, theta is in radians. Right. So a radian is really a linear measure that describes an angle or a central angle of a circle, because as we expand our angle, it captures more and more of the circumference of the circle. Right. So what we're figuring out is how many radius values or radiuses or radii you need in order to stretch around the circle. All right. The length of one radian should be equivalent to the length of the radius. Right. So this is probably a little bit more than one radius. Maybe the radius only gets you this far. All right. This distance here would be roughly equivalent to this distance here. All right. So we would need one, a little bit more than one in order to get us around. Right. But the benefit of doing it that way is it takes the measure and makes it a linear measure, right, with units associated with whatever the linear units are, right? But since it's a ratio, those units cancel out anyway, which is kind of nice. Bottom line is we need that information in order to reconcile the angle in degrees with the length of the radius, because it's apples and oranges until you do that. All right. Now, when they say find the segment of the circle with a radius of 6 feet and a central angle of 108 degrees, that 108 degrees needs to become a radian measure. All right. So 108 is not one of our special angles around the unit circle. So we'll convert it. All right. So 1 degree. Well, actually, let me do it I'll do it the longer way. There are shortcuts, but I think it's kind of nicer to at least understand where this is coming from. So, and we talked about this last time, but very quickly, 180 degrees is the same as pi radians. I need this 180 to become a 108. So what I could do is divide both sides by 180. Right, that's going to leave me with 1 degree is equal to pi over 180 radians. If I want that 1 degree to become 108 degrees, I'd multiply both sides by 108. That makes the left side 108 degrees, 108 degrees. And the right side 108 pi over 180 radians. All right. So this is really just kind of I'm not doing it the long way for the sake of doing it the long way. I'm doing it more so that you can see and really feel where all this stuff is coming from, or what it all means, I guess. You could simplify the 108 over 180 if you want. It's not necessary because we're going to chuck it into a calculator anyway. All right. The area of a segment, again, is 1/2 r squared theta minus the sine of theta. All right. Now, very important, your calculator needs to be in radian mode. All right, calculator must be in radian mode. All right, so we'll do that. Again, you hit home, go to settings. All right, we actually already learned how to convert from one mode to the other. It's just we went from radians to degrees. Now we want to go from degrees to radians. All right, so home settings, angle measure, and just make sure it's on radians. And then you can go back to the calculation menu. All right, so 1/2, they told us the radius was 6. 108 pi over 180 minus the sine of 108 pi over 180. All right, you may wonder why it didn't matter that we were in degree mode or radian mode for the last example, or the segment problems. There was no trig function in there. There was no sine, cosine, tangent, or anything like that. Right? It was just simple calculation. Here, because we're taking the sine of an angle, it needs to be in radian mode. All right. So I'm going to pop it all in. 1/2 6 squared. Power inside or outside, it doesn't matter in this instance. 108 pi over 180 minus the sine of 108 pi over 180. Close it up. Oops, one too many. So this is what you type into your calculator, all in the home screen, which is good. Once you convert it over into radian mode, then everything else that you do is going to be in the home screen, which is, yeah, nice. So nearest 10th. So we're looking at about 16.8 square feet. All right. The ratios in here, the units, I mean, they're kind of hidden behind the scenes, but they cancel away. The units are really associated with whatever the radius value is. That radius was 6 feet. Square the units of feet, it becomes feet squared. All right. Won't always be in feet, sometimes inches, sometimes miles, really doesn't matter. Got a question there? Going once. Okay.
Sorry, I unmuted myself by accident. My bad.
Oh, all good. All right. So the next one doesn't look like it's related to this at all, but it actually is. So we have 5 equivalent segments here. I'm gonna draw, or at least attempt to draw, a fresh diagram here. Diagram being the word of the day. Diagram. All right. So again, I'm drawing a diagram, which is the word of the day. I'm going to call a quick time out here. All right. So that happened, but it's all better now. All right. Yeah. So let me get rid of this extra shading here that I don't want. So we're looking at this little sliver of stuff here. Now, ultimately, we're looking at 5 little slivers of stuff. But we'll start with one of them. All right. Now they tell us the radius is 7 inches. Now they don't tell us what the central angle is, though. All right. It tells us really only the radius, and it gives us the picture. But what we can do is kind of make an assumption here. It's a pentagon, but it looks like a regular pentagon. All right. That we have to assume. In a regular geometry class, there are no assumptions. I mean, just because it looks like something doesn't mean you assume that it is. All right. But for our purposes, we're just going to assume it. On a test, I'd be very explicit. I'd say find the area of the shaded region if a regular pentagon is inscribed. But I wanted to take the opportunity to talk about what a regular pentagon is. All sides and angles are congruent. Okay. So each one of these sides is equivalent to each of the other sides. All right. It also means that each of these angles are congruent. All right. But another property of a pentagon is that if you were to draw line segments from the center to the vertices of the pentagon that's inscribed in the circle, those triangles will all be congruent. All right. They're all going to have the same angles and sides. All right. There are 360 degrees in a circle. But for our purposes, we want to think in terms of pi. So 2 pi radians in a circle. Now, though, that 2 pi or the 360 is getting broken up into 1, 2, 3, 4, 5 different pieces. All right. So if we were to go all the way around, starting here and going all the way around the circle, right, we could even think of it as sweeping through like I do for some of the other problems. I'm starting here and I'm working my way all the way around. that would cover 360 degrees. All right, or 2 pi radians. So each one of them has to be 1/5 of 2 pi in each sector. All right, which is the same as saying 2 pi over 5. All right, that's probably a long, wordy way of saying just take 360 and divide it by the number of sides in the polygon. But again, I like to give the explanation. All right, so this angle here, theta, is 2 pi over 5. And again, the area of a segment, 1/2 r squared theta minus the sine of theta. All right, so we know the r, we know the theta, we could just pop it right in. But again, that's only going to give me one of the segments. If I want the area of all the segments, I'm going to do 5 times 1/2 r squared theta minus the sine of theta. Or 5/2 if you want. So 5 over 2 times 7 squared times 2 pi over 5 minus the sine of 2 pi over 5. So all that goes into the calculator. It's 2 pi over 5 minus the sine of 2 pi over 5. And that would give us the area all in one shot. Area of all of those segments. So 37.4 square inches. All right. And again, my analogy that it's the crust of the pizza, it's not quite. Right. Crusts are rounded, but you know, it's, in terms of a mnemonic, it's not the worst. I think that's all I wanted to say about that problem. The next one is a more practical question. So we're looking at a windshield wiper on a car. It sweeps through, it's 20 inches long, sweeps through an angle of 110 degrees. How large an area does the wiper blade clean to the nearest square inch? So you have, windshield. You don't have to draw a diagram. I'm just doing it for fun. But we're looking at something like this. It's got a fixed pivot point. This would be your windshield wiper. Oh, I did it the wrong way. This would be your windshield wiper. It sweeps through back and forth, back and forth, back and forth. Right. You'd probably have another one. I would imagine most people have 2 windshield wipers. I know on some of the cars now, one of them's like smaller than the other. Like the driver side one sweeps through a bigger area, and the passenger side one is a little bit smaller. But that's irrelevant to this problem anyway, because it's just talking about the one. All right. So what that looks like is a little bit of a wedge. It looks like a sector of a circle. So what I do is I just kind of pretend that there is a whole circle here. And that this is just part of it. So it looks something like this. It's not perfect. I mean, my ability to draw is suspect on the best of occasions. But this would be my center. This angle here would be 110 degrees. And we're looking for the area of that sector. Right? So it's not a segment question, it's a sector question. I'll just kind of put that over there. All right. So that's the other thing, diagnosing which question belongs with, I'm sorry, which method belongs with which type of question. All right. So the radius, they said, is 20 inches. So my radius, 20 inches. My theta value would be 110 degrees, but I need to get that over to radians. So instead of doing it the long drawn out way that I did before, what I can do is just multiply by pi over 180. All right. And that'll give me 110 pi over 180 radians. Now, this one I kind of feel obligated to simplify, only because both the top and the bottom have a 0 in it. So, highlight the wrong thing. So those simplify away. You don't have to simplify. I'm just doing it so that I can type less stuff into the calculator. So this one is just more of a simple sector, which is 1/2 r squared theta. All right. So 1/2 times 20 squared times the theta value, 11 pi over 18. All right. So we don't need the theta minus the sine of theta. If they were, for whatever reason, asking for like this little bit here, this little crust, that would be a different story. But that's not what they're asking. All right. So pop this into the calculator. Oops. I hit answer instead of 1. I don't know how that even happened. 1/2 r squared. Oops. Do it again without the oops. Went off the rails pretty badly. Just do it this way. Oops. Another oops, more oopses. All right. Then we're going to multiply that by 11 pi over 18. All right. So it puts it in simplest fraction form, which is great. We don't need it. 383.97. So they said to the nearest square inch. So that's going to be 384 inches squared. All right. So we didn't have to go to decimal point on that, which is good.
Professor,
Yeah, go ahead.
the blade is 16-inch long. It's just, I guess, extra information that we don't need to look at.
Oh, you know what? I kind of missed that. I don't know what. Yeah, actually, I don't want that. That shouldn't be there. Windshield wiper in a car is. That's actually a legacy typo. That bad boy's been there since the beginning, and it confuses the living daylights out of people. So I ditched it, but I forgot to actually ditch it from the problem. Right. So what the original intent of the question, I'll just show you off on the side. It was really kind of dumb to begin with, but you had a windshield wiper that had an arm that was like a certain distance long, and the rest of it was the blade itself. And so the blade would travel through the area, creating this, but this part of it here would sweep through the area, but it wouldn't clean anything. All right. So this is the windshield wiper arm would move back and forth. Part of it would contain the blade, but this little area here wouldn't clean anything. Right. But that confused people, just the wording of it. So I tossed it. I just apparently tossed it in my mind and not in reality. All right. So get rid of that. I'll try to keep it simple. All right. So got a few more minutes. So we're going to talk about a little bit involving SOHCAHTOA, right triangle trig. You know, we kind of started off discussing it a little bit, but it didn't really go anywhere because we spend a lot of time with the unit circle, which is really important. But then, yeah, at some point we have to come back to it, you know, because it does have value, does have meaning. right? So couple of examples just to kind of remind you of how the Pythagorean theorem works. You know, we did this a little bit, but it's worth taking the time. And then we'll get into the SOHCAHTOA stuff. All right. So the examples at the top, find the measure of the hypotenuse of a right triangle if the legs are 1 and 2. So I'm going to draw a quick picture, even though you draw diagrams as necessary, right? Don't draw a diagram for the sake of drawing a diagram, right? There's very rarely I'm going to tell you that you have to draw a diagram. Most of the time you'll do it just to get an idea of what's going on, right? Rough sketching, you kind of like a doodle, all right? So here it would be a doodle, except I have autocorrect for the shapes, but here's a right triangle. The legs are 1 and 2. I'll put the 1 there and the 2 there because the base looks a little longer. And I'm looking for the hypotenuse. We'll call it X. All right. In a right triangle, the relationship between the sides is that the sum of the squares of the legs is equal to the square of the hypotenuse, otherwise known as a squared plus b squared is equal to c squared. All right. Let me just send this real quick. All right. So I would say 1 squared plus 2 squared is equal to x squared. I could have called the hypotenuse c if I wanted. It really didn't make a difference. All right. So 1 plus 4 is equal to x squared, which means 5 is equal to x squared, which means x has to be equal to the square root of 5. All right. All stuff that, you know, it's not new. All right. When we talked about quadratics, I mentioned this last time, when we talked about quadratics, when we took a square root, we always put a plus or minus. For a standalone geometric figure, you don't need the plus or minus, right? Because plus or minus indicates direction. Here, it's representing a length, which should be absolute, right? So just positive measure. Then we have equilateral triangle. Find the length of the altitude to AB. So here's an equilateral triangle, or at least my attempt at making one. The altitude, the definition of altitude is a line segment originating at the vertex that extends to the base, forming a right angle, right? So a lot of words to represent this, right? It's the altitude to AB. So that must mean that the base is AB, all right? Line segment extending from A to B, which means if it's triangle ABC, the remaining angle, the remaining vertex must be C. All right. They're telling us that BC is equal to 4. The length of the segment from B to C is equal to 4. Now it's equilateral. So if BC is equal to 4, so is AC, and so is AB. Right? One of the properties of an altitude in an equilateral triangle is that it will bisect the base, right? Which means that these two line segments are equivalent, specifically equal to 2. So if I want the length of the altitude, I'll call it H for height. It's Pythagorean, right? So I'm looking for this line segment, which is part of a right triangle. So again, a squared plus b squared is equal to c squared. The two legs are a and b, doesn't matter what order you put them in. So I'll say 2 squared plus h squared is equal to 4 squared. So 4 plus h squared is equal to 16. Subtract 4 from both sides, h squared is equal to 12. H must be equal to radical 12. Right. You're not always going to have to simplify, but just for the sake of refreshing our memories on how to simplify fractions, you break it up into the product of 2 factors, one of which should be a perfect square, right? So you think about the largest perfect square value that divides evenly into 12, that would be 4. And then you say, well, 4 times what equals 12? It must be 3. So we have the square root of 4, which is 2. Rad 3 you can't do anything with. So 2 rad 3 would be the value of the height. All right. This actually adheres to the 30, 60, 90 right triangle rules, but just kind of pretend that we don't know that. All right. Now, the reason why this is important, and we'll get to number 3 in a minute, is in order to figure out all the ratios that make up a triangle, we need to know what all the measures of the triangle are, right? All the sides and angles, right? More importantly, when it comes to SOHCAHTOA, we need to know the sides, but there will be instances where we also need to know the angles, right? Well, that's a different story for a different day. Right? It says the length of the diagonal of a square. So here's my square. I'll call it ABCD. Not by choice, it told me to do that. Right? It says AB is equal to 5, and I need to know the length of the diagonal. Well, in a square, if one side is 5, they're all 5. So 5, 5, 5, 5. The diagonals in a square are congruent. So whether I draw the diagonal from A to C or B to D, it's going to be the same length. So if I figure out one, I figured out them both. All right. So I'm going to use the Pythagorean theorem. And the reason why I know I could use the Pythagorean theorem is because all angles are perpendicular in a square. Rectangles too, but specifically the special case of a rectangle where all sides are congruent, also known as a square. All right, so I'm going to call this X and say, again, A squared plus B squared is equal to C squared. The two legs are 5 each. So 5 squared plus 5 squared is equal to C squared. 5 squared is 25, plus another 25 is 50. Square root both sides, you get rad 50 is equal to C. And then again, simplify it. For now, it's just practice, but later on, you'll see why. The largest perfect square factor that goes into 50 is 25, 25 by 2. So this is going to be 5 rad 2 is equal to C. All right, square root of 25 is 5. Can't do anything with the rad 2. All right. Now, the 6 trig ratios, they all relate the measures of the sides. Okay, so I'm going to diagram this up. I'm going to call this some angle theta. And for trig ratios, you can work in radians or degrees. Just be mindful of what the question's asking. Sometimes it'll say radians, sometimes it'll say degrees. So you need to be flexible enough to go both ways. All right. For the 6 trig ratios, we start off with the basic 3, which is sine, which is opposite over hypotenuse, cosine, which is adjacent over hypotenuse, and tangent, which is opposite over adjacent. All right. So from the perspective of theta and the right angle, we can identify the opposite side and the adjacent side. All right. So the hypotenuse is the one that's opposite the 90-degree angle. The one that's opposite the value of theta, or the angle theta, that's going to be the opposite. So that's O for opposite, not a 0. The other one has to be the adjacent. All right. So what we're doing here is finding, we say the 6 trig ratios. It's really all the ratios that make up a triangle. So all possible ratios. And a ratio is just a division between 2 measures, right? So if I take 2 numbers and divide them, I've created a ratio. I want to do that for all possible cases, right? So if I start off with from the perspective of A, for example. All right, I can create ratios involving A. I can take the A and divide it by the H. I can take the A and divide it by the O. if I change my perspective so that I'm starting with the O, I can take that O and divide it by the H. I can take the O and divide it by the A. If I change my perspective so that I'm looking or I'm standing at the hypotenuse, I can then take the hypotenuse and divide it by the adjacent, or the hypotenuse and divide it by the opposite. All right. These are all the different possible ratios that I can create. Somewhere along the lines, they decided, you know what, that opposite over hypotenuse, let's call that sine. Actually, do this real quick. Opposite over hypotenuse, we're going to call that sine. Adjacent over hypotenuse, we're going to call that cosine. Tangent, opposite over adjacent. And then we have the co-functions, cosecant, secant, and cotangent. Now, there are geometric relationships between these things, but for the time being, we're just going to look at them as reciprocals of the first three functions that we came up with. So cosecant would be the reciprocal of the sine, h over o. Secant would be the reciprocal of the cosine, and cotangent would be the reciprocal of the tangent. All right. So if you're looking for kind of a simple way to think about this, it's really basically saying we have all these ratios, they all exist. If I told you that a triangle had sides 2, 3, and 4, and I wanted you to state every possible ratio that you can come up with, you'd say 2 divided by 3, 2 divided by 4, 3 divided by 2, 3 divided by 4, 4 divided by 2, 4 divided by 3. 6 possible ratios. All right. We're just throwing a name on them here. All right. And we end up with SOHCAHTOA as being the most prominent one. But really, the three most important trig ratios, sine, secant, and tangent. All right. Those are the most important ones. Those are the ones that are without the co. All right. So those are, I mean, it's been presented that sine, cosine, and tangent are the three basic trig functions. The three most basic trig functions are sine, secant, and tangent, because everything else is related to those three. It's just historically people teach it this way, and sine, cosine, tangent, SOHCAHTOA. I'm guessing it's because of the acronym. Somebody along the line said, "Oh, we could say SOHCAHTOA. It's going to be so easy for them to remember. Shouldn't we use secant instead of cosine?" No. It's not going to flow as well. SOHCAHTOA. That sounds weird. I don't think it does. I think it's perfect. SOHCAHTOA. All right. But they decided SOHCAHTOA. Maybe it's the consonants. They wanted some extra in there. But yeah, these three are the most important ones. And you'll see as you go forward into calculus, that's the case. Right. But we could also find, and this is the last thing we're going to talk about tonight, we could find a missing side in a trig function if you know what the angle is, right? But we can also find the angle if we know at least two of the sides, right? So this one is the directions I've been meaning to change on this. Find the length of, or find a measure. I'm just going to get rid of all this. Of angle theta in the figures below. All right, so find the measure of angle theta in the figures below. All right, so the perspective is important because you'll see that in some cases it changes. It all depends on where the hypotenuse is, and I guess indirectly or directly, depending on what the right word is, where the right angle is. All right, so what we do is we identify the reference angle, which is theta, and name everything in relation to it. All right. So this is my hypotenuse because it's opposite the 90. This one's my opposite. And this one is my adjacent. All right. So the two that I care about would be the 5 and the 12, because those are the two that I know. I don't know the hypotenuse. Now I could solve for it easily enough, but I don't need to in order to figure out what theta is. Right. So I have an O and an A. The ratio, the two possible ratios I can create with an O and an A. One would be the tangent function. Tangent of theta is equal to the opposite, the O, over the A. So I would say tangent of theta is equal to 5 over 12. All right. Now to figure out what theta is, well, first I need to decide what mode I want to be in, right? They didn't tell us one way or the other, so I have a choice. I can go with degrees or radians. And at first you might say, you know what? Forget this radian stuff. I'm going to go with degrees. It makes more sense to me. I've been working with it for years. You will be better served in the long run if you go radians. All right, just putting that out there. So if I want to find, and I got a whole unit on inverse functions, but for now, I'm just going to say very simply, if I want to find theta, I'm going to apply a rule. All right. And we did this in unit 1. Rule. If the composition of a function and its inverse is equal to the argument, which is in this case x, then, and actually let me make that a g. If you compose two functions and the result is just whatever the variable is, then f and g are inverses. All right. So without knowing what an inverse tangent is, we can still apply it. All right. The reason we can apply it is because there's a calculator function built in. All right. That'll do it for us. So what I'm going to do, because I want to get theta alone, I'm going to take the inverse tangent of both sides of the equation. So inverse tangent of both sides of the equation. On the left-hand side, it's the tangent of theta. On the right-hand side, it's 5 over 12. Applying this rule up here will yield or lead to just a theta as a result. And then all I'd need to do is figure out what the inverse tangent of 5 over 12 is. And you'd say, well, great, thanks. How do I do that? The A tangent button in your calculator. So in NumWorks, NumWorks, we would say A tan of 5 over 12. The A stands for arc. It's arc tangent. And that's what I meant before when I said I got a whole lesson on inverse trig functions. And it's the reason for that, or the reason for it is that. So I would hit A tangent, so shift tangent. It'll say arc tan. And then I would just put in the 5 over 12. All right. Now, in the upper left-hand corner of my calculator, you could see it says rad. So I need to remember that's going to give me the indication of what kind of answer I'm going to get. All right. So I get 0.395. This is rad, or like we could do the power of R if you want. All right. If you want it in degrees, same computation, just got to kick it over into degree mode, which I find to be a royal pain. So I don't do that. You know, you can get the degree measure. That's great. I don't think it added anything to the conversation. Right? You want to start thinking in terms of radians anyway. I like to think in Star Wars when they're in the Millennium Falcon and and Han Solo yells out, "We got TIE fighters coming in at 0.2." I'd like to think they're talking about radians. Right? I never really researched it, but like if you say something, like there's a bandit at 4:00, that gives you an idea. As opposed to saying there's a bandit at 120 degrees. Well, actually, I think, yeah, that might be 120 degrees. It doesn't really flow as well as saying it's coming in at 4:00 or at 6:00 or like whatever, right? But in Star Wars, they say it as some decimal value, right? They could very well be talking about radians, which I think it would be pretty awesome. All right. Although if you told somebody you're like navigating a plane, and it's like, oh, okay, so we want to be facing 0.4. You're like, what are you talking about? They want degrees in real life, but for the purposes of the math computation, we want radians. The next example is pretty much the same concept. I wanted to do, well, actually, you know what? I'm going to change it because I can. We're going to make this the hypotenuse. All right, so pretend this wasn't there. All right, so still perspective, but now the relevant sides, again, hypotenuse, opposite, this is the adjacent. The two that I know about are the opposite and the hypotenuse. All right, so that leads me to the sine function. So sine of theta, which is opposite over hypotenuse, would be sine of theta is equal to 7/11. All right. By finding the inverse of both sides. And I'm just going to create a little room here. So inverse sine of both sides of the equation. And again, the reason we're doing this is so that based off of the rule, if you compose a function with its inverse, it's going to cancel to just whatever's contained within the function, in this case, theta. So then I just need inverse sine of 7/11. All right. So second, thinking TI, shift sine brings up arc sine, type in 7/11. Hit OK, and you get about I'll say 0.690. All right. The next two I'll save for next time, but I am going to change the examples again because every one of them was a tangent. So that doesn't really help. So I'm going to make this one, I'm going to put the 3 here, and I'll put the 2 here and wipe out the 2 over here. And well, I guess one of them has to be a repeat because if we're going sine, cosine, and tangent, you could, and I'll also show you next time how we could have used cotangent for number 1 and cosecant for number 2. All right, but that's probably a little too much for now. The last one, number 4, I'll just leave as is. So I'm going to put stars on these two, and that's where we're going to leave it for today. So let me stop the recording. I'll leave the share.